So in the last lecture, we had looked at antennas and what different properties affect our observations and how to control them, right? So we went into the details of electromagnetics of antennas and radiation patterns and so on and so forth. So today, as I said, we will split our lecture into half and half. In the first half, I'll talk about rest of the system, which is not antenna. That's called, the full thing is called radiometer, where you're trying to measure an absolute value. So this is different from, say, interferometers, where you are trying to measure fluctuations. And oh, thank you. Yeah, thanks. You should. Thanks. Yeah. So basically, radiometers are designed to do absolute measurements, unlike the fluctuation measurements that interferometers do. So suppose I had antenna and I connected that output directly to an oscilloscope. Oscilloscope all of you have used. Okay. So what do you expect to see? Suppose like now you know that there is an electromagnetic field that's incident. It produces basically some kind of a voltage at the antenna, and that output you feed to a oscilloscope. So you're looking at the voltage that is produced as a function of time. What do you expect to see? Go ahead. Sinusoidal wave. It's a function of time. Why? Oh, okay. That's okay. Well, also look at the time scale, but good guess. Anything else? Oscilloscope. It's real. We'll actually see noise, nothing else. Uh, in time, sky signals are seen like doing noise as a function of time. So then you might ask the clean, nice data that we just talked about before, where does that all come from? So if you have a very bright source, your RMS goes up. Or basically your variance in this, what we call is the power in the noise, that goes high. And therefore, if you look at the distribution, you will end up getting a Gaussian. These are all Gaussian random noise. And what you are interested in the time domain is the variance of this noise. That's all. At the raw level, that's what it is. And why this is important, I'll come down to later. But anyway, typically when we want to build a radio telescope, how do we get started with this? So what's the first thing that we have to put? And what do we connect to antenna? That's antenna. Sorry? Resistor. What for? Huh. Sure. So assume that's this. There is some resistance in the wire. No, radiometer, a single element system. Low noise amplifier, though that's specific. Why low noise amplifier? No, this is correct answer. Right? You need to, I mean, amplification, yes, we require because these signals are very weak. We all say, oh, foregrounds are bright, but we need to know what that brightness is. It's very faint. It's fainter than a snowflake. So we say in astronomy, relatively everything is bright and everything, but you need a signal boosting. If you did not have an amplifier, you would not see anything. So you need something to boost the power of your signal, which is amplifiers. And you'll probably want to boost it by a factor of 1,000 to 10,000 minimum in order to even able to see what is coming. But by low noise, that ln is low noise, A is amplified. Huh. Right. Great. That's exactly what the point is. That this should not contribute to already noisy sky signal. Great. What else? Why? Sorry? Yeah, go ahead. You want to select those frequencies. But yeah, because this is all time stream data, right? That will have all the possible frequencies, which is also what you are saying. Right. So basically what you need is, once we have boosted the signal, you want to narrow down the frequency range, right? So for example, for our experiments of cosmic dawn, epoch of reionization, what's the frequency range again? So let's get that number. Sorry? 50 to 200 millihertz. That is correct. So the simple calculation that you can do is, cosmologically, you are looking at redshifts of what? The frequency at which you will observe this will be 1420 point something. So you can compute for redshift of 6 what my frequency should be, for redshift of 40 what my frequency should be. What does that come to? Sorry? 200? What's the lowest one? 30, okay. Roughly, yeah. So 30 megahertz corresponds to the highest redshift, and 6 corresponds to the highest frequency here. So you need a filter. You basically want to design. Great question. Yes, I'll get back to you. Why? Order matters. This might not be the most optimal order. There are pros and cons of the order. But yeah, so we want to filter out the frequencies so that we only observe things which are between, say, 30 megahertz to 200 megahertz. Rest of which we don't care about. So it's what we call as a band pass filter. It only allows frequencies in this range. Okay, so you boosted the signal power. You have filtered out the unwanted frequencies. What next? The data is still in the time domain. Sorry? Integrate. Who said integrate? Integrate. Why integrate? Reduce the noise. Okay. And finally, you have to digitize it. I mean, because till now, if you just again tap the output of this, you will still get this. It's time domain data. So you have to, after these two steps, which you have rightly guessed, the last step is basically some kind of a analog to digital conversion you have to do, because eventually it has to come to this lab, right? So you basically then sample it and sample it high enough that you are able to reproduce the signal, and finally you do some kind of an FFT. So time domain converts to frequency domain, and that's the kind of spectra that you see. So everything that we talked about till yesterday was an output of this. So this is time to frequency domain conversion. The volume matters. So when you start storing time domain data without averaging, the volume builds up very quickly. So yes, in principle, for example, when you do very long baseline interferometer measurements, you have one telescope in Europe, one telescope in Asia. You actually do that. You literally record the raw voltages and bring that other raw voltage and correlate them offline. But it becomes a very huge storage problem. So you would ideally want to do FFT on board just to reduce the data volume. Because there is a time integration that happens before doing FFT, which is inbuilt in the digitizer aspect. So you average, accumulate data for some time in time, and then do FFT. So you are saving on this. Yeah, if you don't average, then yeah, the volume remains the same. Yeah, you can. So yeah, after averaging whatever time domain data you have, yeah, if you have an 8K point of FT, you have 8K time samples, 8K frequency samples. It's just that we have the processing to do it right here. So after averaging, you have a choice. So there are these offline correlators also. But I'll talk a bit about this. What goes on? There's something called field programmable gate array (FPGA). This is like a mini computer. So it has a nice resource to do everything on board. So eventually you can see the spectrum, because when you're also conducting observations, you may want to see what you are getting instead of realizing it one day later after you have done offline. Things like this. But in principle, what you're saying is correct. One can store raw voltages and then do everything offline. Yeah, it will. So there's something called quantization error, right? Because you are discretizing the whole thing. So the way to reduce that is basically sample it at very high cadence. You have more number of samples for that range of frequencies. So there is something called Nyquist sampling, if you've heard. So if you are, say, going till 200 megahertz, if you sample at 400 mega samples per second, your quantization noise will be very, very low compared to all other systematics that we have discussed. So those aspects also come in. Any other questions? Okay. So till now, everything is fine. You took the antenna, you recorded some voltages, you amplified them, filtered them, digitized it, FFT'd it, got the spectrum. But the signal is not periodic. So you so you do some kind of a taping before you do the FFT. So that process is called windowing. I did not really include it here. But right, if you have a sharp boundary, then so that sync will come in. In digital signal processing, there are something called window functions. Look it up. So people have tried playing around in the time series. Once you have the data, you might want to wait it before you do the FFT. Similar to TG, yeah. But here is windows. But so, for example, in Saras, you do something called Blackman et al. Window, and then do FFT. That's a technicality I didn't want to get into, but that's a good question. If you do raw FFT, you will have a lot of side loop contributions. So you want to condition your signal before you do that. On board. Yeah. Because once you have an FFT, it's already windowed. You have to do windowing in time before you do the FFT. So what you get here is already processed through that, so that the inter-channel leakage is minimized. Okay. So yeah, they have boosted it, filtered it, digitized, got a spectra. Next. Yeah. So basically, if you have, say, in time domain, you have an RFI. Now what happens is, if you are not doing any weighting, you are doing a top hat weighting by default. So when you Fourier transform, you will also get the response of the top hat, which is a sync function. So basically now that RFI will come at one frequency, but because of this sync function, it will also have its contributions at other channels. But there are better ways. So instead of a top hat, you can use some very customized weighting. In that case, when you take the Fourier transform, you will see that the side lobes are down by 80 dB, 90 dB, and so on. So then your spillage will be small, and then you can treat each frequency as independent. Which not just the window size, but also which function you have used. So there are Hamming windows, all kinds are there. This is one of the most important topics in signal processing. So yeah, you got the raw data, but it doesn't have just what came here, right? It also has everything that got contributed on the way. So what do you do about it? How do you undo these effects? What you want to really see on your data is what was here, right? You don't really, this is nuisance. Radiometers are nuisance. It's just that you have to use them, but eventually you want to undo everything. And that process is what we call as calibration. Right? So calibration is a very broad umbrella term which deals with removing instrument related imprints on the data. It can be multiplicative, it can be additive, it can be direction dependent, it can be direction independent. There is a whole forest of systematics. And we'll just address one in this lecture, but you can talk to me later about how we deal with every different kind of it. Right? So when you calibrate this radiometer, I have categorized it in some aspects. Response comes from the antenna. This is what we have discussed in plenty. So you have instrument responses coming from the primary beam because of its frequency dependence, and also what we call as the return loss yesterday, which is the impedance mismatch. So those will also imprint something to your incoming sky signal. So by the time it reaches here, it already has effects from the antenna. After which, and these are direction dependent effects, especially primary beam, because again, your chromaticity might be different in different directions. So anything which is imprinted by antenna or ionosphere, they are all clubbed together called a direction dependent systematics, which is this. Okay. The next one is basically each of these modules have their own what we call as gains, right? So I said we are boosting the amplifier by a factor of 1,000 or a factor of 10,000. So that number can also be frequency dependent, right? So at say 40 megahertz, you are boosting it by a factor of 1,000. At 100 megahertz, you might be boosting it by a factor of 10,000. It's not a flat response. That is what we call as band pass. Many of you must have done band pass calibration in your interferometric data sets. And basically that comes from your analog devices, your digital systems, even digitizers also have the band passes. So you collectively want to correct for all the band passes. It can be loss, it can be a gain, doesn't matter. At the end of the day, you are multiplying your signal by some cumulative G. And that G can be different for different frequencies. And the last part of systematics are additives. These are very tricky to deal with. So how can additives arise? So these additives are not related to sky signals. They are related to some other source of power in your system or around your system. So one source of power is the medium around the antenna. Right? So your antenna is not in the vacuum. It is on a ground which is at some ambient temperature. That will also couple. In dishes, for example, that is called ground leakage. Of course, for elemental antennas like dipoles, they will be even prominent. So they will also couple through the system the same way sky couples. So you will have, and that will basically manifest as additive. It's not really sky multiplied by something, but ground multiplied by something. And the last bit in the additive is the noise here. So that's why I think someone said you want to minimize noise. That's why I say low noise. What happens? This is also a source of power in your system, and it can create standing waves here. The reason is the impedance is not really matched at these two ends. So you can imagine a signal going back, getting reflected from the antenna, coming and doing this multiple times with more and more delays. So you will have an interference pattern very nicely built in. So just to summarize, additives are basically it's sourced by two things. One is from the medium around the antenna and one by what we call as receiver noise. And multiplicatives come mostly from your band pass and a bit from antenna. Yeah.
The bodybuilding of the players that they have this little wire on the ground. So is that to increase the
Yes, precisely. So that's why a lot of antennas you will see have huge ground planes. That is to suppress the contamination.
Also, AWM
Same reason. So you would ideally want to reduce your additives. So ground coupling can be reduced by increasing the metal size. It's the same. So in some way it boosts the antenna efficiency, but the major reason is the ground coupling. Okay, and but just caution also. When you put the ground screen, your L by lambda becomes very big because ground is also part of antenna. So you will probably have more frequency dependence in your primary beam. So you're reducing this, but you're increasing this. So you need some kind of an optimal arrangement here.
Reason for using water.
That's very specific to Saurabh. The reason is this only, by the way. You want, like, ground coupling again is not a straightforward term, and I'll get there in my second part of the talk. Fine. So this is just a class of different systematics. In this particular lecture, I'll only focus on the middle one because that's the easiest. That's what band pass calculation. So what you're trying to do is you're trying to correct for these things. So how do you do that? How do you calibrate interferometers? Many people have done here. Look at a bright source. That's only actually. So I'm not looking for more answers. You look at a bright source. Now the problem with global experiments is you can't look at a bright source. And the reason I told yesterday, when you have a compact sources, because of your primary beam size, its brightness gets diluted by the solid angle of the source to solid angle of the beam. And that's a huge dilution. So you can't use point sources for calibration. Instead, what we do is we inject a known calibrator source. So it's like we create our own point source. So I just added one more thing, which is a calibrator. It basically produces noise, and we characterize and make sure it's flat. So that once you look at the antenna, this is a switch. So once your rest of the system is connected to the antenna, it takes in the sky signal, then it toggles to the noise source. It takes in the noise source data, which is flat, and you can toggle that noise source on, noise source off, so that the powers are different, and propagate it through the same thing. Right? So let's simply work out what this will do. Why do we want to use something? So let's see. For 1 second, we are taking the antenna data. So let's look. So what we are measuring, I'll call it TM. So TM1, this is when the switch is connected to the antenna. Right? So you have TA. Now TA will be multiplied by the gain of entire system. I'm collectively calling that gain as G. This is independent. I'm ignoring that subscript. Right? Plus, you have an additive that's coming from things that we already discussed. So this is what you are measuring at the output of FD. And what you are interested in is in TA. So what you have to solve for are these two. What is capital G? What is the gain of my system, which is bandpass calibration? And what is the additive part? To get TA. Now for this, we go to the noise source. So now the switch has gone to the noise source and then has cut off. So your second measurement, TM2, will have the noise source. Noise source can be on and off. The only difference is it's a flat as a function of frequency, but the total power can change. So in one case it is on, the gain remains the same, and additive remains the same. It's only what is coming as the input signal changes. And you take a third measurement where your source is off. So how do we get TA now? If you have to solve for G and A, if you can eliminate them, that's also fine. Sure. The T off is not zero, actually T off is 300 Kelvin. It's at ambient temperature, it's not cooled. In off state, it will have 300 Kelvin. In on state, suppose it has 1000 Kelvin. So what we can do is we can subtract these two. So TM2 minus TM1. TM3. Right? Now, what we can also do is subtract the first and the third. Yeah. I mean, that's why I said 1 second. You don't expect your system to change in 1 second. Yeah, if you put in 1 hour, so these are the three spectra that it got. Everything is offline here. So I subtract the first, the second, and the third. I get this. I subtract the first and the third, and I get this. Let's divide one by the other. Let's do TM1 minus TM2. So by taking the T is gone, your A is gone. What you are left with is TA minus the noise source off, which is typically scaled down by noise source on minus noise source off. Now these two terms, on and off, you have to measure in the lab. There is no other way. So suppose on minus off is on it's 1000 Kelvin, off it's 300 Kelvin. This number becomes 700. So whatever you have measured as TC, you multiply this by 700 and you add back your 300, which is the T off. And that will basically give you the antenna temperature.
Between the T in on and T in off to be as large as possible.
It should not saturate the system. But ideally, yes, you want a large. So your T will be, I'll just call it delta T, which is noise source on minus off, plus here now. So this is just a very common model of how to calibrate for the band pass. Same thing is done for interferometers actually, when you have a bright point source.
Realistically, when suppose all these components, if they are mass produced to be identical to the best of all, does calibration of one work for all, or do we have to calibrate all of them?
All of them. Even within a single batch under ideal conditions, the gains are never the same. We have seen that in the lab also. You order 10 amplifiers from the same company, they will have different gains. Yeah. Great. Just like the same as criteria of point source. Your point should be stable. It should not vary with time, right? You choose sources which are stable on the sky. Your noise source power should be roughly the same. And more importantly, it should be flat. Because again, if it has say some kind of a spectral structure, you in the process of calibration, you are basically propagating that to the antenna temperature. So the criteria is it should be very stable across a range of temperatures and its spectral profile should be constant. No, it's out after that. Yeah. So noise source is like a device of this size. You can directly connect it to a switch. Someone else had a question? Hmm. You were,
Same noise source for all.
right. So typically arrays don't use noise sources again because it becomes very complicated. We use point sources. For interferometer, you are sensitive to point sources. You can for each antenna you can look at the calibrator and you can solve for gains of each element separately. That you can correct for because you exactly know that separation. So for example, in sky based or yeah, that's why the gains have to be separately solved for. You can't assume the two gains of two different antennas to be the same. All those factors will play out as different gains of the different systems. Even in the redundant calibration where everything is assumed identical, you don't do this. You have to solve for G1, G2, G3. separately. For each antenna, it has to be different. For global experiments, it's just one antenna, so it doesn't matter. In your interferometer techniques, have you done redundant calibration, sky-based calibration? That might be a whole lecture. Okay. Any other questions? Time variation of their gains. You basically toggle this very fast. So suppose your gain is changing every 5 minutes. So within that 5 minutes, you should get the noise source data. You should also get the sky data. So that whatever variability is there, it's the same in the board. As long as the gain remains the same between antenna and noise source, it's fine. So typically for interferometers, you do 1 hour or 2 hours. Now the gain variations may happen in those time scales, but you would still want your calibrator to be close by than your target field. Same here. You basically want them to be as close in time as possible. So in Saurabh, for example, we do in every 1 second. 1 second on antenna, 1 second on noise source. So any kind of a gain variability is accounted for. Any other questions? Yes. Yeah, precisely for the same. So secondary calibrators are all close by because you want little gain drift. And gains can drift because all these modules are very sensitive to temperatures. And the temperature keeps on changing, so their gains will also keep on changing. So you have to calibrate often enough. Okay. If there are no questions, this is just how this looks like in real. So I'll come to why it's on water. This is Saras at RRI. It's exactly this with some modifications. So you have an antenna. It's a disc cone antenna, something like monopole. This is our amplifier and filters, which is this part. We call this analog receiver. And then we have the thing that does the digitizer and the FFT. This is called digital subsystem. So these are all connected. And essentially you get your output from it. So this is just a sketch of how things work out in real life. Why does it float on lake for this specific experiment is simply because the third thing that I mentioned here, ground coupling. Ground coupling can come from different layers also. Each is the different dielectric. It's not a uniform medium. So you have to model the coupling from each layer up to a lambda at least. And that lambda is 6 meters at 40 megahertz. So then electromagnetically, you have to know the dielectric constants for each layer, conductivity for each layer, which is difficult. While on water, it's like a one uniform medium, and you can easily measure the conductivity and dielectric constant. So modeling the additive part gets much easier. Okay. Fine.
Then you need that much depth.
Yes, absolutely. You need depth. So we go for like 10 meters or so, at least. Higher the better for us. Okay, so this is how it looks. I'll probably not get into the detail of the next slide. Basically, how this transforms when you actually want to do a global 21 centimeter experiment. It's like this. So it has more complications than just this, but just take it from me that the basic principle remains the same.
What you see,
This CNU, additive. So I wrote it A there. Okay, it's additive. Oops. So that is determined by what's your highest frequency. So in our case, we go till actually 250 megahertz. So we sample at 500. It has to be at least double. Otherwise, your reconstruction will not be proper. And I'll exactly come to this point next. Okay. So I'll not go into the details of this system. Yes. What is?
I mean, in the previous slide, we have which things are floating on the water, right? Which are
Till here it's floating. Only this part is at the shore, and they are connected via optical fiber. So you have seen here, this floater is there. Essentially, there is a 100-meter cable, an optical fiber that goes all the way to here. So, this whole system is a single piece.
this magnetic analog signal to optical.
That's right. Okay. I mean, I didn't want to go through it, but after amplifier, you have this electrical to optical converter. Stability of you anchor it, and you don't observe when it's windy. That's pretty much it.
I can also sit on it.
Yeah. Crocodiles can also sit on it. Yeah. So you have to pay a lot of attention. You have to anchor it very properly, all the way to the down, and make sure that the lateral movement and other kind of wobbling things are not there. That's why you have to be on lakes and not really oceans. Where it can.
Indication that you're going to deploy it next program.
Yeah. I mean, not sure, but yeah.
How would you prevent?
We don't know yet. I mean, we are still looking for sites. But one of the major things is stability of the antenna is. I mean, you can't compromise that. We'll see how it will go. Anyway, but that's basically how these instruments look like in real. And now I think you're able to appreciate better about the calibration aspects. Yes. Other medium space. That's really the best one, because instead of a uniform medium, you have a vacuum. So like ground, I think it's like this: ground is the worst, then water, and then vacuum. 10 meter above the ground. If you can make your antenna stable there, it's fine. The only problem is it will see more RFI. It's but possible, like balloon experiments, right? But then the only problem is your antenna has to be stable, and there should not be a metal for suspending it, because then it also becomes part of the antenna. Yeah, experiments are challenging. Okay, so the last part before I switch gears completely and make it a presentation instead of a lecture is sensitivity. I think whoever has done observations here has seen this at some point, but I want to derive it very quickly. So you saw the system: you have antenna, you have analog, you have digital, and your signal flows. How long do you have to observe to get to where you want to get? Right? So this is what we call as radiometer equation. And it's such a simple but elegant equation. This is specific to single element systems, but you can also extend this to interferometers. So before I go into this, let me ask. In the labs, you all have done measurements of time period of pendulum or some other method. Typically, when you do such things, you do it for more than once. You do it at least 5 times, 10 times. Why? Reduce the errors. So how does it reduce the error? You take the average. But how do you know that the averaging is going to reduce the error and not increase it? Assuming that the noise is Gaussian. So what's the special property of Gaussian noise that helps us? But what is so special about Gaussian errors that when you average more and more samples, your errors go down? Yeah. So, and you can actually derive it from its PDF, right? Which is what you want to do is minimize the variance. The standard deviation. So the standard deviation, if for a single measurement, suppose you are measuring time period of a pendulum, your measurement is the t plus sigma 1. And you took n such measurements. And then you averaged it, as you said. What will be the error on the average? So where does root n come from? Absolutely correct. It goes down by root n. So where does this root n come from? Deriving. It's a nice statistics problem. It's very elegant. You start from PDF of a Gaussian distribution and convince yourself that when you average multiple n number of independent samples, independent is the key word, your variance will go down by this. So same thing happens in radius term. I started off with that plot, right? That in the time domain, all you will see is noise, and the spread of the noise or the variance will be determined by your sky signal. So basically, going to the very first plot here. This one, right? So what you want to do is reduce the fluctuations. Therefore, you have to average more and more samples. So what determines the scale of the fluctuation here? It's zero mean always in time domain. But what determines the uh, RMS or the standard deviation of this? For a simple radiometer we discussed. Right. So let's go through it. Antenna temperature. Yes. So it depends on what's coming from the sky. What else? Because see, it's proportional to total power. Antenna is one part of the power. What other sources contribute? Ground, we just discussed. Ground is also a source of power. Impedance, receiver, our LED has some noise. You can give one idea. There are lots of terms. Each is subdominant now. So this whole thing is called thesis. So it is, I think, slightly misleading when we say it's a system temperature, because then people tend to think it's only a system. But system temperature really has everything. Antenna temperature you can also decouple into T21, foregrounds, CMB. So system temperature is essentially sum total of every power that you can measure. Right? So in some way, the noise that you saw, the variance of that noise will be thesis. Thesis is the system temperature. Now, this is a fun question. And this is just with Gaussian statistics. So when you have a measurement, you have a mu, you have a sigma. The error on mu is sigma. So mu plus minus sigma. What is the error on sigma? Everything has error bars.
How many samples you have got in the
Okay, suppose when
system?
so in the final answer, your mean will have the error of sigma by root n. What is the error on sigma by root n? Okay, again, it's a very fun exercise. It will be root 2 of sigma. That these are the statistics, nothing to do with radius. Error on sigma is root 2 sigma. So the reason I brought this up is it becomes very easy now to derive this. So for a noise statistic, your variance is root 2, and the spread we have is the system temperature. So this is basically the variance that you have measured just from one sample. Now you want to reduce it, and all of us in this lecture will agree that you have to average more, and that's it. So you can average in two ways. You can average in frequencies and you can average in time. The only thing is they have to be independent samples. So time is straightforward. So total number of samples is, suppose you are taking the observations for some t time. So you have some say t samples separated in time. So over 1 second you have taken say for the frequency. And just take it from me. I don't think we have time to do a more rigorous thing. If you have in your data frequencies up till nu, the number of independent points in that is 2 nu. That's why you have to sample it at 2 actually. Essentially, the final RNS will be your initial starting off, which is root 2 of thesis, by square root of number of samples, which is that gives us this. And you'll use this like a bread and butter.
You can repeat what you said about why.
Yeah, so basically when you're sampling a signal, how many independent points are there for a Gaussian statistic? If you have signals still new, like you have frequencies from u1, u2, u3 up to nu. For each, say you go to highest of un, your number of independent samples will be twice that. That's why when you want to sample, I said you have to sample it twice the frequency of the highest, twice the highest frequency. They are related things. Look up Nyquist criteria if you want to study this better. So that's why there is a factor of 2 there, 2, not new. So you get this number. So all it says is very simple. Your total power is say 1000 from the sky, 1000 Kelvin, 100 Kelvin from your system, another some few Kelvins from here and there, make it 1200. Your system temperature is 1200 Kelvin. You have some bandwidth. That bandwidth can be say 1 megahertz. And then you integrate it for some time, which is say 1 hour. So then you can compute that once you get your measurements, what's going to be the uncertainty on those measurements. That is sigma t. And that is nothing but the sensitivity of your radiometer. Right? So let's very quickly do that exercise. So let's say my thesis is 1000. And my frequency is 1 megahertz. And my integration time is 100 hours. What is my uncertainty?
That's a coming from that.
Nothing to do with complex actually. The top square root comes because your error on variance is root 2 times sigma. And the bottom one is coming because the number of independent samples are 2. So there's nothing square in like real error maximum. That plays a interval.
In the case of any counting, like gene counting, that follows Poisson distribution. Here it is
Central limit theorem. You have lots of samples. So for example, in Ceres, you have integration of how many points? You're sampling at 500 megahertz, so microseconds. You're converting to milli. So roughly 1000. You have a million integrations in one. So even if individual errors are discrete, just by the sheer number of samples you are averaging, it becomes eventually a Gaussian error.
it's also like counting.
It's a counting experiment, yeah. Just the numbers are very large compared to this. So you can safely assume Gaussian statistics.
Each count is very interesting. Each time step. Basically, it is Poisson, but it is close to Gaussian.
It's very close. I mean, when we have done Gaussianity tests, it really stands all the tests. Yeah. Did anyone try it? Just order of magnitude. 10 raised to 10 raised to minus 6. Minus 3 is more reasonable. Minus 3. So 1 millikelvin. That's it. That's all you need for global experiment. Right. So what I wanted to show is, if you just look at this, see, you need millikelvin sensitivity, right? Your measurement should have plus minus 1 millikelvin accuracy. You can easily achieve that in 100 hours. And 100 hours is not a big deal. If you're observing for 10 nights, each night you're getting 10 hours, you're done. You have a good global signal. Right? So the point that I want to drive across, the sensitivity is not a problem here. We say, oh, it's a very high sensitivity experiment. But technically the sensitivity is not very hard. Like you just did it. 100 hours is sufficient. what you really need to control are your systematics, because unlike noise, systematics don't average. So if you have done any issues here in your calibration, they will stick up on above your 1 millikelvin that you have computed. So that's it. Then you'd observe 100 nights, 1000 nights, doesn't matter. You will be stuck there. And that's the state of all the experiments. Okay. So that's a nice transition in the last 10 minutes to show you this. So this is just fun, no blackboard. No. So till now you understood how antennas work, how radiometers work, how do we calibrate it to some extent, and to what kind of sensitivity we can go to. So we are at these places. So there are different experiments in global 20-liter community. Saras is here in India. We keep on changing, so this is not really a good pointer. But when I made this map, we were here, so I put it there. We have a few experiments happening in South Africa. So the commonality that you see is these are not criticized, because one challenge we don't want to face is radio frequency interference. So you would ideally want to go to places which are remote. So we have EDGES experiment in Western Australia. I think the most exciting one is this. This is called Marian Island. This is midway between South Africa and Antarctica. So 2000 kilometers both sides. So Marian Island has an experiment going on. We have another one coming up in the Atacama Desert. There is one at the LWA. This is Owens Valley. Recently, there was also a setup done at the Arctic in the Canadian very high latitudes. And then we have our own experiment that keeps on drifting here and there, but mostly in Ladakh. So yeah, this is a landscape of different experiments. Yes.
Name. The name of this experiment.
Right. I'll tell you. Which one do you want to see? You want to see Reach? Reach is from South Africa. Yeah. So that's there. There are two experiments in South Africa, Reach and High Z. This one and this one. Okay. So Bighorns, well, it's not anymore, but it was in Australia. EDGES is in Australia, Western Australia. Vida is currently in Owens Valley in US. Sci-Hi again goes to different places. It was in that Marian Island I mentioned, right here in middle of Antarctica in South Africa. But this is the same experiment has gone here. And then we have Saras here in India. And MIST is the new experiment coming up in Atacama Desert. So, and of course there are more. These are the current set of experiments. But I already know there are people who are trying to build more experiments around the globe. So this number will probably increase by a lot in next few years. No, this is actually just 2 hours from Bangalore. This was more of a test deployment. Yeah, so the first contrast that you see is how different all of these antennas are. Right? That really shows we have not converged on what the best design. So we all think there are different ways of doing the calibration, and calibration is the bottleneck. Like I said, sensitivity is not a problem, you just compute it. So how you calibrate better is the question. And all of these different experiments are trying their own ways. So where? Owens Valley. Oh yeah, LWA. Long wavelength array. Yeah. This is one of the LWA antennas, which is being used in the single element. Okay. So yeah, and Saras is here. In August, this was in Ladakh, now it's back in Ararat. And we are planning another one in April. We also have another experiment, and this is basically coming to space now. So these were all ground-based experiments. We also have space-based experiments. Well, not experiments, but proposals. And the reason is, I think now appreciate better all these challenges that I just wrote. So you have interference, you have ionospheric effects, you have the additives, All of that is eliminated by flying this, right? So instead of banging your head, modeling all of that, where? Yeah, RFI you can control by going to basis, but what we have also seen is they are all getting worse. They are not as good as they were 5 years back, for example. Poor. Yeah, I mean, you have to then move. There is little you can do. For example, if there is civilization has come up somewhere, you ask them to stop their electronic devices. So then you move to some other place. Yeah, possible. So if the RFI is not persistent, if it's in chunks, for example, in Ladakh, we see till midnight there is a lot of RFI, then it kind of dies. So you only see data which is clean. But there are sites which is persistently bad, then you can't really do much. Yeah, right. So that's the beauty of cosmological signals, right? They are all sky. They don't really depend on what part of the sky you are looking at. Foregrounds will change, but signal remains the same. So you just use the cleaner chunks of your data. So even in orbits like this is lunar orbit, and we know far side of the moon is very radio quiet. But it will be orbiting. So at some point you will face Earth and you will see RFI. So idea is only do observation when it's far side. So there are not just Earth. So this is called Pratyush. This is again at RRI. But there are also other space-based experiments that are proposed. Okay. But this is what we call it the mainstream. There are other experiments. I can't go into the details of these experiments, but there are other ways to do global measurements. It's not just single antenna. So people actually use interferometers. There's an experiment called Assassin. It's in Australia. That's trying to do using MW antennas, interferometric measurements, trying to measure the monopole, which is very challenging. But it has its advantages. People have also tried looking at polarizations. So basically taking the advantage of the fact that your foregrounds are polarized, your signal is unpolarized. So there is this experiment called cosmic twilight polarimeter. It's a very nice concepts, all of these, but they are still, I would say, very elementary stage. Most of the experiments are basically trying to do a typical single element objects. Yes, your systematics are uncorrelated there. When you cross correlate two different antennas, your additives, for example, are not correlated. So you gain there, but there are issues also. Right, I mean, there's no UV coverage. Like you are always sampling the origin because it's a total power experiment. There is no baseline. So you're always sampling origin. It doesn't matter where the antenna is. So in some way, you're only measuring the total power, not the fluctuation. So yeah, people have also proposed a constellation of satellites. There the UV coverage becomes important because what they want to do is float a set of satellites, and because their baselines are continuously changing, you will keep on sampling different points in the UV space. Yeah. So there are proposals. I think the China Space Agency is launching also for the for radio interferometers in space. Oh, I'm not aware. Okay. Okay. Sunrise mission. Sunrise is mostly for sun. So, but that's a phase direct. So I think it's not like different satellites which are all concurrently. It's still, I think, one system but with multiple feeds. Something which lines. But there have been proposals. There is an OFAR from Europe. Anyway, yeah, there are proposals. Space is very attractive simply because of these challenges. Can I steal 5 minutes from you? Thank you. Okay. So just to show how clean the space is, this was the last lunar mission that did a radio measurement was Radio Astronomy Explorer. This was 60s and 70s. This is a few megahertz. With the x-axis is time, y-axis is the brightness. This is when the Radio Astronomy Explorer was seeing the Earth. This is when it entered far side, and then it came out. And these are different frequencies. So you see how clean the far side is. For how long we don't know, but for now it's clean. So that's why all these proposals are being pushed towards launching lunar observations around the moon. This is Radio Astronomy Explorer. It has its own antenna. It's not functional anymore. Yeah, it was orbiting. So this is Earth facing, this is far side, then Earth facing. Okay. So I don't think I go into the details of this. I thought I'd touch upon them, but I'll just run through them. And yeah, it can observe every time, but you have a ground coupling there. You don't even know lunar ground. But having said that, there are proposals. So there is an experiment called FARSIGHT, which is a literal flying arrays on the lunar surface. There is something also called LCRT, Lunar Crater Radio Telescope. So there is a crater. You basically put your dish there, make like Arecibo, and use it for cages and stuff like that. There is a very nice talk at RRI on 2nd January, online if you want to attend, on the Lunar Crater Radio Telescope. So yeah, space is attractive, and so is Earth-based experiments. Very quickly, in the last 2 minutes, I'll want to focus on what other things that have been done in the global community, like 21 centimeter community. What is foregrounds? So till now, we have really been looking everything from perspective of the 21 centimeter signal, right? But you can also do spectral index measurements. You all did that in the tutorial. And edges, Saras, LIDA, we have all tried that. And what we found is existing sky maps had huge calibration errors. So now we have provided a recalibrated map for those all sky maps that you saw. And this is all coming primarily from these 3 experiments. And now they're part of the corrections when you download those from NASA or other websites. So that is one bonus science, which is you can get to categorize foregrounds better because your systems are more accurate. Other thing is ionosphere. Ionosphere is actually a wide field of study in other fields. And again, it's a challenge for us, but we can characterize and contribute some to that community. So for example, this is bighorns. You subtract the mean off. And as a function of time, you see your spectra fluctuating. And this is solely coming from ionospheric fluctuations. The total power is changing. Using this, you can characterize the electron temperature. So edges, bighorns, for example, have done this. So you can study ionosphere, you can study foregrounds, and you can put all kinds of upper limits on the value of 21 centimeter signal. So this is coming to the core science, right? So you can look at 21 centimeter, what's the amplitude? And there have been different constraints on the extent of reionization, the redshift of reionization, coming from all different experiments. I can't go this in any more detail, so I'll skip this. And the last part, as I said, or maybe you know, which was the detection, which I think some of us knew, which is a signature like this, which has been since refuted by us. So that happened. And the last part, which I really want to focus is, at this point, you can also try combining different things. So you can do power spectrum measurements, which Krishna taught you, and you can do global experiments. It actually helps because eventually you're looking at a parameter space of exactly parameterized. You have to look at the properties of the galaxies, you're looking at the velocities, so on and so forth. You can combine all the likelihood. So the systematics are very different in these different experiments. The way you calibrate are very different. So when you combine them, your constraints improve. That was basically the message I wanted to drive across. And we have done this for combining power spectrum measurements from Hera, Ceres measurements, and we have tried to constrain different properties of these galaxies. And some of the nice constraints were actually drawn from radio and X-ray luminosities. And you can extend this to other measurements, MWA, low power, edges, all different experiments you can put together in the same kind of a frame. And I'll end with this, which is, it's a very active area of research, and there are lots of things happening. Lots of things are happening at the instrumentation front, as you I think appreciate more. You have to design better radiometers, right? So what kind of antennas, what kind of calibration strategies one has to do. But at the same time, something that we may not have discussed in a lot of detail is you have to do really well with your analysis. And so, for example, program models right now, the kind of things we use are very model dependent. You have to assume some physics, you have to assume some spectral property. How can you be more independent of those assumptions? Systematics are a big deal, and there is a whole forest. When we say systematics, it's not a monolith. It has all different categories. How do you effectively model all of them through a common Bayesian framework? That's something. Towards the theory side, when you do parameter inference, you really have to sample your parameter space very quickly. And as you might have appreciated from Kanan's talk and Girish's talk, simulating this 21 centimeter signal is a big challenge because you have to compute so many properties on a grid. So you need that turnaround time to be very quick. So people have tried, say, emulation or machine learning techniques to do this. That's also a very recent development, and I think it's a very active research area. And the last is that you can also try doing synergy. I think that's a nice transition to his next talk, which is you can combine different measurements, but because eventually you are looking at the same field of 21 centimeter brightness, right? So you can look at different measurements, try to combine them to enhance your constraints. So with that, I think I'm already over time. So thanks everyone. And if you have any other questions, you can always write